Hi everyone, today we'll look at some techniques of differentiation. Like I said in the last lesson, there are some times that we can't differentiate like what we did in the previous lesson. Alright, so today we'll be discussing implicit differentiation, logarithmic differentiation, and parametric differentiation. Alright, so we'll start with implicitly defined function. First of all, we need to know what is the meaning of implicit. Okay, implicitly defined function means your function cannot be explicitly expressed in one term. Like for example, this fish looking shape, the equation is x cubed plus y cubed minus 9xy equals to 0. Alright? So if I want to differentiate, usually I will write y equals to something in terms of x, right? But for this equation here, do you think that we can like take out the y then put x at one side? It's like very hard, right? If we try to do it, okay, if we try to do it, y cubed, we throw the x cubed to the other side. Alright, seems good. Then we factor out the y, 9xy, this one we have a 3. We've tried to factor out the y, we have y squared minus 9x, right? Then y equals to negative x cubed. You see, we have a problem here. We always have a y that on the other side, right? So this is what we call implicitly defined function. We cannot explicitly express y in terms of x. Similarly, if you look at this circle, oh by the way, the equation of this circle is actually x squared plus y squared equals to 25. Alright, if you want to argue that, oh, actually you can, right? Y squared equals to 25 minus x squared. So y will just be plus minus 25 minus x squared. However, when you differentiate, which one should you choose? Without knowing the value of... No, actually it doesn't matter because it is actually not a function, it is a one-to-many relation here already, right? Okay? So, if you look at this diagram here, the one in yellow, you actually take the positive version of it because it is above x-axis. While the one in blue, we will take the negative version of it. And actually, if you want, then you can go ahead and differentiate all dy, dx at x equals to some value here. Okay? Then you go and find the slope at this one, for example. But for this kind of equation, which is implicitly defined, we can actually do what we call the implicit differentiation. Alright, so the direction to do implicit differentiation, the steps is very easy. First, you differentiate both sides of the equation with respect to some variable, and usually in this lesson we'll be differentiating with respect to x. Then when we differentiate, we will treat y as a differentiable function of x, which means like look at this fish example. We have x and y stuck together, right? So if x and y are stuck together, and we are now treating y as a differentiable function of x, means it is something like a composite function, isn't it? And in differentiation, when we talk about composite function, the first thing that comes to your mind should be chain rule, right? So we'll make use of chain rule during our implicit differentiation. Then after you differentiate, you will collect all the like terms, all the terms with dy, dx, put at one side. Then you will solve for dy, dx. So this is the direction. And I will show you how in the next example. Okay, let's look at this example, a very simple example. Like I said, if you want to do implicit differentiation, alright, you will differentiate everything with respect to x. Okay, let me just write down this one. You differentiate both sides, right? Means you differentiate every term. And you see, this is an implicitly defined function because you see x and y stuck together. Okay? Sin xy. And now what? Now, go and differentiate. Okay, now your y is a function of x. So you try to imagine this y squared as something square. So remember, when we talk about chain rule and general power rule, we will just differentiate Bring down the power minus 1, so it is 2y. There's something else, right? We need to differentiate inside. Am I right? But do we know how to differentiate y? Because we don't know y in terms of x, right? So we don't know, just write like this, d dx of the inside function, which is y. Can you see it? The outside function is the one in blue, okay? This one, blue square. Then I bring down the power minus 1. Then differentiate inside. I don't know how to differentiate y. So I put d dx of y. Okay, then for this one it's very easy. Because you see this x and this x, no problem. Plus, how about this one? It's again chain rule, right? You differentiate the outside function. The outside function would be cos xy times, you differentiate, inside is a product rule. Am I right? It's a product rule. So you differentiate the first, you copy the first function, differentiate the second function. You want to differentiate y. Again, don't know. d dx of y. Then plus, copy the second function, differentiate the first function. The first function is x. Differentiate x, you get a 1. So just like that. Now what? I will tell you that this fella here and this fella here, they are the same, which is our friend dy dx. Right, I mentioned I think the last, in the first class, where we talk about the notation. d dx of y is equals to dy dx. And now, see magic here. Cos, maybe I should expand it. X cos, xy cos xy. xy cos xy, am I right? dy dx plus y cos xy. Am I correct? Oh no, sorry. X cos xy, sorry. X cos xy. This one grouped together already. Okay, this one becomes dy dx. And now, remember, we need to do the second step. Collect all the terms with dy dx to one side. So I will shift this term here to the other side. 2y dy dx, I'm running out of space, minus x cos xy dy dx equals to 2x plus y cos xy. And now, factor out your dy dx. So dy dx will be, this one I copy. I'm running out of space, so I'm skipping one step, yeah? This will be 2y minus x cos xy. And this is it. And this is it. How we differentiate implicitly, because the question only asks us to find dy dx. So this is the answer. Alright, so let's move on to the next example. Okay, so for implicit differentiation, we also have higher derivatives. Alright, so the higher derivatives is actually the 2y dx squared. Normally what we do is actually we differentiate the dy dx, right? We differentiate again the dy dx. So it's the exact same thing over here. Okay, so we'll do it very quickly. And if you notice from earlier, there is some kind of shortcut here that you may realize, which is if the variable agrees, means like this one, x and x, then we just differentiate normally. If the variable disagree, like this one, x and y, we still differentiate normally, then we put a dy dx. Yeah, so this is a pattern of implicit differentiation. Variable agree or variable disagree. And this is because the variable disagree part is because of the chain, the chain rule. Okay, so for this one, 2x cubed, variable agrees, right? Differentiate normally. 3y squared, variable disagree. Also, differentiate normally, but put a dy dx at the back. Constant, differentiate becomes a 0. And this one very easy, dy dx. You move this over, move that over, will be x squared over y. Okay? But the thing I want to talk about in this example is actually the second derivatives, d2y dx squared. Like I said, you will differentiate, okay? You will differentiate dy dx. And who's your dy dx? This fellow here, d dx of x squared over y. And obviously, because now both x and y are actually functions, y is a function of x, so you need to do quotient rule. Okay, quotient rule. Copy bottom function, differentiate top function, variable agrees. Copy top function, differentiate bottom function is a 1, variable disagree. Okay, then bottom function square. Then we just go ahead and simplify this. But before that, what is this fellow? dy dx. Is this one now? You just plug it in. So there will be 2xy minus x squared times x squared over y squared. Okay, then we'll just go ahead and simplify this. 2xy minus x to the 4th over y squared. I want to get rid of this layering, so I multiply both top and bottom by y. So it's a 2xy squared minus x to the 4th over y cubed. And if you want, you can also split it into two terms, which is 2x over y minus x4 over y cubed. Also can. Okay? Okay, now we'll do some exercise, which is not as simple as just now because we will now have logarithmic, exponential, and trigonometry all together. But don't worry, like I said, just check whether your variable agrees or disagree and just differentiate normally. Okay? Derivatives for ln is 1 over y. Variable disagrees. It's a product rule here because everything is function of x, remember? Copy first function, differentiate second function, plus copy second function, differentiate first function. Variable disagree. Rearrange. Bring this over. E y sin x dy dx ey cos x. Okay. Solve for dy dx. 1 over y minus ey sin x. Make sure you have all the terms, yeah? But this is still not nice, right? Because you still have like layering like that. So multiply both top and bottom by y. Y ey cos x over 1 minus ey sin x. Y ey sin x. Okay? And that's it. Exponent again, trigonometry again, chain rule again. Okay, so differentiate normally. E 2x, chain rule, differentiate 2x, you get a 2. Variable agrees. Chain rule, differentiate outside function, differentiate sign, you get a cos. Copy whatever inside. Better put a bracket. Differentiate inside. Differentiate x, you get a 1. Variable agrees. Plus constant multiple. Differentiate y, you get a 1. Variable disagree. Okay, then I think you better expand this bracket before you do the shifting. So actually no need, you know, because it's only one term that you need to shift. So I directly do plus becomes minus cos x plus 3y. Okay, times 1, right? Equals to 3 cos x plus 3y dy dx. Then I just solve for my dy dx. 2e2x minus cos x plus 3y over 3 cos x plus 3y. This is it. Okay, next one. Okay, we have a product rule inside, product rule outside, and we have a cos inverse. Do you remember what is the derivative for arc cos? Never mind, just do it. Product rule. Copy first function, differentiate second function, and differentiate inside we have another chain rule, okay? Cos is negative 1 over got square root, start with 1 minus whatever inside square. Then you need to differentiate inside, right? Okay, differentiate inside is a product rule again. Product rule. Copy first function, differentiate second function, you get the 1, variable disagree, dy dx. Plus, copy second function, differentiate first function, you get a 1, so that's it. Okay, and remember, you are still doing your product rule. We have another product rule, outside product rule. Copy second function, differentiate first function, which is y, differentiate get 1 times dy dx, because variable disagree. Then you just go ahead and simplify this. Negative xy 1 minus x square y square then dy dx, right? Dy dx plus cos inverse xy dy dx. I move this over, yeah? Y times y, negative become positive. Y times y is y square over 1 over x square y square. So let me move on to the next page. Okay, dy dx will just be, I think I better write this one first. Okay, y square over square root 1 minus x square y square. Be very careful, yeah? You factor out dy dx, so it's 1 over whatever you have here, which is negative xy 1 minus x square y square plus cos xy. Okay, and now what? You need to simplify. Not simplify, like you need to get rid of the layering. Like I always said, you get rid of the layering. Square y square, multiply both top and bottom by x square, 1 square root of 1 minus x square y square. So on top we'll have y square square root of 1 minus x square y square over square root times together becomes 1 minus x square y square, negative xy because this and that cancel, plus square root 1 minus x square y square cos xy. Finish. Okay. So after doing these 3 questions, after I told you the variable agree, variable disagree, that pattern, there is actually one more shortcut for implicit differentiation. And actually I made a video somewhere in September or October last year. Okay, which is this one. Dy dx is equals to negative fx over fy, where your fx is del f over del x and fy is del f over del y. What is this symbol? This is actually partial derivatives. And in fact, this one is actually from your Calc 3 lah. Just some concept from Calc 3, but it will make your life easier. So in simple words, when you are doing partial derivatives as the shortcut for implicit differentiation, for this one, partial derivatives with respect to x, you will treat all the y as constant. Okay? Then for this one, you just treat all the x as constant. Okay? I will show you one example, maybe from just now this question. Ln y equals to ey sin x. Okay? ln y equals to ey sine x. So the first step is to clear everything to one side, okay? Which means I will shift this one to one side. And it doesn't matter, you want to shift ln y to the other side, also can. Because the goal here is actually to make a function in terms of x and y. And this is a multivariable function. I told you already, this is from Calc 3, which is multivariable calculus. So this is a multivariable function. Alright? And now, you just write dy. You want to find dy dx, right? dy dx negative del f del x means you go and differentiate this further here, treating, okay, let me let here, treat y as constant. Now your ln y is constant. You differentiate constant, you get 0. Minus, initially when you are doing implicit differentiation, you were doing product rule for this one, right? But now, no need, because e to the y is a constant. So now it is constant multiple rule instead. Then you just have to differentiate sine x, which is now cos x, over del f del y. Del f del y means you will treat x as constant. You also differentiate this one. So now your x is constant, your y is a variable. Differentiate this one, you get 1 over y. Minus, now ey is your function. Sine x is a constant. Okay, sine x is a constant. Then you differentiate ey, you still get back your ey times with a constant. But this is still not nice, right? Because you still have layering. Just one more step to simplify. Negative, negative, and positive. Y cos x over 1 minus ey sine x. And this is it. Okay, you can actually check your answer. This one and what we had earlier. Yeah, see, they're the same. Okay, so if you are interested in this shortcut, which is like partial derivatives, particularly for implicit differentiation, how it works, how we derive this formula, you can go ahead and watch my video from last year. It's actually about partial derivatives and chain rule again. Okay, so it's up to you which one you want to use, but if you are talking about second derivatives or higher derivatives, it's actually all the same. All of them will be very tedious. Because you see, from just now we got a question about second derivatives, right? It is already a quotient, so you know that you definitely need to do quotient rule. So for this one, also need to do quotient rule. So it's up to you which one you like to use. Okay? But for a Cat 1 student, unfortunately, you can only use the conventional method, unless it is MCQ. Okay? So now we'll proceed with the next one, which is logarithmic differentiation. It sounds so, wow, so amazing, right? Logarithmic differentiation, what is this about? But actually it's very easy. Just do one more step before you differentiate, which is you take the natural log on both sides before differentiating. Why? Because we want to simplify the formula with the laws of logarithms. Laws of logarithms means this one. Okay, if you remember from when we talk about transcendental functions, you have product rule, quotient rule, reciprocal rule, power rule. So what we mean by simplifying here is either you take the ln so that the power can flies down. Power flies down. Remember what we did when we derive all the commonly occurring limits? We keep on taking ln on both sides, right? Because we want the power to flies down. So same logic applies here. We want to simplify, we want the power to flies down, so we take ln on both sides. And another thing is that from the laws of logarithm from just now, you'll notice that the product, whatever you have inside, You see, whatever you have inside, ln of something inside, you can split it into the sum of two terms. So instead of doing product rule, now you do sum rule, which is definitely simpler. Similarly, instead of quotient rule, you will now do difference rule. Alright, so we'll directly do the exercises. Okay, now I see. If you want to do it, if you really want to do this conventionally, you'll either do product rule plus chain rule, and inside I got another chain rule again, which is very complicated. But if you do logarithmic differentiation, you see, I'll show you, it's very simple. Just take ln on both sides. Remember, this power half, right? Or maybe I should write one more step for you. Square to the half. This power flies down. Flies down to where? Here. Okay? Then you just actually one more thing you can do. Okay, ln y, like I said, product now becomes sum, right? Because of the logarithmic rules. Oh, and this one is another thing that you can bring down the power. 2 times half becomes 1. Okay, then you just differentiate. Variable, disagree, constant multiple. Write down whatever inside, differentiate inside, 1 over whatever inside. But the difference between logarithmic differentiation and implicit differentiation from just now is that you need to write dy dx explicitly in terms of x. Means you cannot have y in your answer. Why? Because you see, originally your y is already can express in terms of x explicitly, meaning your dy dx also must be expressed in terms of x explicitly. So you need to bring this 1 over y over, which is you multiply the whole thing by y lah. And who's your y? This one. So this will be your answer. X minus 1 square times... Oh, you can actually simplify this and that, you know. X over x square plus 1 over x minus 1. Yeah, there's nothing much you can do. Okay, please check if I make any mistake. So this is it for logarithmic differentiation. We'll do more example. Okay, the next one we have trigonometry, and like I said, no worry, just tag natural log on both sides, and you can make the product and quotient into sum and differences. Alright, so ln y equals to ln theta is a product, becomes sum, right? Quotient becomes difference, and then power flies down. In case I'm too fast, I think I should write one more step for you. Ln y equals to ln theta sine theta over secant theta power half. I'm actually doing this one. Then I go split this into 3 terms. So that it's easier for me to differentiate. See, 1 over y, variable disagree, 1 over theta, variable agrees, plus 1 over whatever inside, differentiate inside, variable agrees, constant multiple, whatever 1 over whatever inside, differentiate inside, tangent theta. Simplify. Bring the y over. Y is this one, the whole thing here. Theta sine theta over square root of secant square secant theta. Copy. This is cotangent minus half tangent theta. Finish. Of course, the answer is still very long, very complicated. But if you want to do quotient rule, chain rule, you'll get the same answer, and it's even more tedious to do that. Alright, so because our goal is only to find dy d theta, so you can use logarithmic differentiation to make your life easier here. Okay, move on to the next example. Oh, this is what I want to talk about. You see, you see, look at it. Logarithmic differentiation. We take ln on both sides, right? Ln y sine x dx. But does it make it easier to differentiate? No, right? Because your problem is with this x to the x. After you take ln on both sides here, if you take it here, it's not helping. So the problem is with this one. Hence, you should take ln, you should somehow make like ln x to the x so that this one can fly down, become x ln x. It's not so bad, like it is a product rather than a very complicated, very scary exponent x to the x. So you just focus on that particular part. What you can do is to use chain rule. You let the whole thing here be u. So it will just be y equals to ln. Sorry, not from here. It's actually from here. See, I make a mistake. From here, y equals to sine u. Then dy du equals to cos u. You just need your du dx, right? And who's your u? U equals to x to the x. This is when you do your logarithmic differentiation. Okay, so 1 over u variable du variable disagree because you are doing with respect to x equals to, like I said, this one is x ln x, product rule. Copy first function, differentiate second function, copy second function, differentiate first function. Remember, bring your u over. Who's your u? Is x to the x. U equals to x to the x. This one, simplify 1 plus ln x. And that's it. dy dx is dy du times du dx. dy du dx. So cos, who's your u? X to the x times x to the x times 1 minus ln x. Finish. Okay, so this is it for logarithmic differentiation. Just one more step before you differentiate, and you need to be very clear which part of the function that you want to simplify. Okay, don't go ahead and just take ln on both sides. Target what you want to simplify first. Okay, now we'll look at the third one, which is parametric differentiation. And I think some of you have learned parametric equation before, right? And let me just go through the definition and the concept, the idea very quickly. So parametric equations, actually you have your x and y, and x and y can be defined using a same parameter. In this case, it's a t. Okay, so if you look at this definition here, you see x equals to f of t, y equals to g of t. Then you have the set of points x, y, f is equals to f of t, g of t. Defined by this equation are called a parametric curve. Means when you plug in this value, you trace them all together, you get a parametric curve. And usually this curve can be a straight line or a parabola or circle, ellipse, hyperbola, those kinds of conics, right? So the idea of parametric equation, maybe I just go through, give you a very simple analogy. Okay, so if you have a very tall building, and someone stand on the top, and maybe this is the cover corporation office. Okay, and this guy is called like Yago. Then you have, suddenly one day you have a dragon, okay, a dragon push him, and he fell from the top to the ground. Okay, and if you study physics, you know that your displacement got two components, right? In this particular motion, and it's projectile motion. I know you have your horizontal displacement sx. You also have your vertical displacement sy, and both of them can be calculated using the kinematics equation, the four kinematics equation. All right, and two of them have one parameter, one equal same parameter, which is the time t. So you can actually draw a table of value. You can plot a table. When t equals to 0, you see your ycos is still here, right? So x equals to 0. When t equals to 1, maybe move 2 meters to the right. 2. Maybe 2, then 4, 3, 6, and so on and so forth. This one I just simply give values, okay? Then what about y? When t equals to 0, it is still on top. So maybe 100, I don't know. Then after that, at t equals to 1, drop down to maybe here, okay? 50. I just simply say that. Then 25, 12.5, And of course, you know this one just I give random values, okay? You know that this is actually free form. A equals to 9.81 meter per second square, okay? This is a projectile motion. Okay. Given that this is a projectile motion, you should know that the shape of this one should be a parabola, isn't it? Should be a parabola. Because of it is a projectile motion. Projectile. And now, if you look at this table here, you can actually express x in terms of t, right? A function of t. If you are doing physics, your kinematics equation, your t is a variable for both sx and sy. But that is not enough, because now I want the equation of this parabola. How do I get that? I need the coordinates of x and coordinate of y, right? If I put it into a coordinate plane like this, okay, x, y. Okay, so I need to get rid of the parameter from here. I need to get rid of the parameter, which is t. So I need to combine two of them together to give me one equation, y in terms of x or x in terms of y, or even if they are implicitly defined also can, as long as I get rid of all the parameters, only x and y. Then I can trace my shape of parabola. And the good thing with this parametric equation is, number one, you can set your own interval using the parameter. Like I said, from t equals to t from 0 to 3. Then you know that it's from here to here. Okay? Instead of having x and y, like if I want to set, I want y to be from 0 to 100, but I don't know when is y equals to 0. I don't know, right? I don't know when y is 0, I don't know what is my x. But if I'm using t as to set my interval, it'll be so much easier because both x and y can be defined in terms of t. This is the first advantage. The second advantage of this parametric equation is that you can trace the direction of motion. Like in this example, I know that when t equals to 0, it is here. X coordinate is 0, y coordinate is 100. When t equals to 1, it is somewhere here, x coordinate equals to 2, then y equals to 50. Of course, diagram not drawn to scale. Then after that here, then here, then here, then here, then finally here. So I know that the particle or yago is falling downwards like this, from top to bottom. I know he is falling. Instead of I just have the shape of the parabola, and I don't know whether he's falling down or flying up. Okay, so this is the idea for a parametric equation. But all of this is not important, because what we want to focus today is how to differentiate parametric equations. And your life is very simple because you already have the formula here. And this formula is actually derived from the chain rule, and it's very simple. You see, dy dt times dt dx, right? From a chain rule. If you want to flip this one, dx, isn't it what we have in the formula? dy dt divided by dx dt. Okay? So you have to be very careful that your dx dt is not 0. If your dx dt is 0, this will be divided by 0, which is something that cannot be done. Okay? Then what about higher derivatives? When you are talking about d2y dx square, okay, d2y dx square, even without parametric or whatever, you know that you differentiate your y prime, and your y prime is actually your dy dx, am I right? So this is just, instead of dy dt, you see, you replace your y with y prime. So it will be dy prime dt over dx dt. Yeah, actually this one. So you have to be very careful. This y prime means the whole thing here. Okay? Then at the bottom is still dx dt. No worries. Okay, we'll straight away do some exercises. When we'll explain what we need to do along the way. So we need to find the equation of tangent, then we need to find the second derivatives. In order to find the equation of tangent, we need two things, which is number one, the slope of equation tangent, and we need at least one coordinate, right? So what we do is we go and find the slope first. Slope means first derivatives. First derivative means dy dx. Dy dx, we need dy dt and dx dt. We already have our x in terms of t, y in terms of t here. Just go ahead and find dx dt, dy dt. And actually, if you just want to find the slope, you can directly sub in the value of t here already. But because I know that I need to find second derivatives, so I will write out my dy dx properly in terms of t first. Okay, dx dt 4t cubed 4t t squared. This is my dy dx, and I will need it later. Okay, then now I need one coordinate, right? At t equals to -1, x, y is, you put in this -1 into this equation. 2 times 1 is 2 plus 3 is 5. Similarly, you put in this into here, you get a positive 1. Then what about the slope? It's dy dx when t equals to -1. Okay, just put in, you will get a positive 1. Then my equation of tangent line, y minus y1 equals to m x minus x1. Y equals to x minus 5 plus 1 is 4. This is my equation of tangent. Then the next thing I need to do is to find the second derivatives. So I will go to a new page. d2y dx squared is, you differentiate this thing here, you need to differentiate this dt of t squared over dx dt. dx dt is 4t. 2t 4t half. So d2y dx squared at t equals to, just now was what? -1 equals to half. Finish. Okay. We look at the next example. Oh, we have sine and cos, slightly more complicated. Okay, and we have t equals to pi over 3. Same thing. Find your dx dt and dy dt first. 1 minus cos t 0, minus minus become plus. dy dx dy dt over dx dt. Then at t equals to pi over 3, your coordinate, okay, this one you put it here, pi over 3 minus sine pi over 3 is secθ 3 over 2. Then 1 minus cos pi over 3 is half. 1 minus half is half. Okay. Then the slope is dy dx at t equals to pi over 3. Sine pi over 3 is secθ 3 over 2. Right? Over 1 minus cos pi over 3 is half. So this one bring on top, it is actually secθ 3 over 2. This one is a half, bring on top, this and that can cancel, equals to secθ 3. I think I write this because I'm running out of space already. Okay? Then the equation of tangent y minus y1 equals to m x minus, you know where I got this value from, it's actually here. So y equals to secθ 3 minus secθ 3 times pi over 3, minus becomes a plus, secθ 3 times secθ 3 is 3, 3 over 2 plus half is 2. Am I right? Miss out x here. Okay, so this is the equation of tangent. Next, second derivatives. d2y dx squared, you go and differentiate this one. But I think we should differentiate separately first because it is already very complicated. It's a quotient rule there already. So dy prime dt, we go and differentiate this one. Let me copy it first. dy dt cos sin t 1 minus cos t. Okay, we'll differentiate this one first. dy prime dt is copy bottom, differentiate top, minus copy top, differentiate bottom, negative and positive. 1 minus cos t squared, cos t minus cos square t. Oh, this one very nice. Why? Because this one basically means like this, right? You know what is this? Pythagorean identity tells you that this equals to 1. And cos t minus 1 is the same as saying I factor out a negative. 1 minus cos t. And I think you know why I want to do this. Because this and sorry, not this one. This and that can cancel. Negative 1 over 1 minus cos t. Then what about the second derivatives? Okay, d2y dx squared, dy prime dt over dy prime dt dx dt. dy prime dt was this one, right? Negative 1 over 1 minus cos t over dx dt is 1 minus cos t. Oh, very nice. Cos t. So it will just be negative 1 over 1 minus cos t squared. Then at t equals to pi over 3, this will be negative 1 over 1 minus half square, negative 1 over 1 over 4, negative 4. Finish. Okay, so just like that, just a little bit more work, and you need to be very careful which one over which one, differentiate which one is your d2y dx squared. Okay, just be a little bit careful, you should be able to do it. Okay, let's look at the last question. It's an implicitly defined parametric equation. This one you have no choice because you see your x and t are stuck together, so you have to do implicit differentiation anyway. Let's look at how we do it. Okay, it's actually very easy. Actually, I can see it already. So differentiate implicitly. You want dx dt, so you differentiate with respect to t. Variable agrees, right? Ln 1 over whatever inside, differentiate inside. Variable disagrees, variable agrees. We want what? Dx dt. X minus t plus 1. Oh, wait, let me see. For this one, right, because the question only asks us to find the slope, we don't need to find the second derivatives. So you can actually substitute in your value of t now. And you will see why later, because if you don't do it now, when you put in your dy dt, you will have a lot of things to substitute. Okay, so now I will just write at t equals to 0. This one, yeah? You put it into this equation. 0 equals to ln x minus 0. So x equals to e to the power 0, which is 1. Okay, then I just put in here dx dt when t equals to 0. X is 1, t is 0, plus 1 equals to 2. Alright, then dy dt, this one very easy. Just normal product rule. Copy first, differentiate second, still get the same thing. Variable agrees. Copy second, differentiate first, variable agrees. No need lah, this one, just like that. Then just directly put in t equals to 0. 0 plus e to the 0, which is 1. Okay, so dy dx at t equals to 0 equals to dy dt over dx dt. And this is it, the slope at t equals to 0. Alright, so this is all for the techniques of differentiation that I want to discuss, which is implicit differentiation, logarithmic differentiation, and parametric differentiation. That's all for today. See you guys in the next class.